Okay, so this is an example of a Kirchhoff's nodal analysis. Usually in a Kirchhoff's nodal analysis, they're talking about a circuit that has two supplies. And they would be asking you to get the current through and the voltage across a load resistor, like this resistor here. So Kirchhoff's nodal analysis involves Kirchhoff's two laws. So Kirchhoff's current law, where the currents entering a junction are equal to the currents leaving a junction. So if you look at this 8-volt supply, the positive side of the supply is this long bar. That's the positive side there. And if we decided this was V1, then it would generate a current I1. Similarly, for this other supply, that's the positive side there, we could decide that's V2, and it would generate current I2. Then the currents entering this junction would be equal to the currents leaving this junction. And the currents entering this junction would be equal to the currents leaving this junction. And that would be the Kirchhoff's current part of this. The second part, voltage law. To prepare to do this, we're going to label all these, they're not junctions, corners. And we're going to look at the closed loops. So closed loops, there's a closed loop here, A, B, E, F. A closed loop here, B, C, D, E. And a closed loop right round the outside. So looking firstly at loop A, B, E, F. Kirchhoff's voltage law is that the supply in the loop must be equal to the voltage drops in that closed loop. So the supply in that loop is 8 volts. And that should be equal to the voltage drops in that loop. Now remember that V is equal to I times R. So the voltage drop across this first resistor here would be I1 times that 8 ohms. So that's V equals I times R. For the second resistor in this closed loop, it would be I1 plus I2 times 4. And that would be that first loop. We're going to expand on that in a wee minute. The second loop we want to look at is loop B, C, D, E, or this loop on the right-hand side. In this loop, the supply is 16. And now you've got the voltage drop across here. I2 times 10. And again, the voltage drop across that load resistor. And now we're going to expand these brackets out. 8I1 and collect like terms. And do the same for the second one. The sequence in the second one's a wee bit different. And remember, you're keeping your I1s together and your I2s together. And you're left with two equations that you should recognise as being something that you can solve using simultaneous equations. So that would be your next step. So your first step is to use your Kirchhoff's current law and work out where these currents are. Your second step is to look at these loops using Kirchhoff's voltage law. And then the next step we're going to go through is solving these simultaneous equations. So I'm just going to write these down again. So my first one, 8 equals 12I1 plus 4I2, equation 1. And my second equation, 16 equals 4I1 plus 14I2. Now I'm going to solve these by multiplying my second equation by -3 so that when I add them up I get rid of my I1s. So I'm going to do equation 2 times -3. So 16 times -3, 48, or -48 rather, is minus 12i1 minus 42i2. And that's equation 3. Then I'm going to add my equation 3 and my equation 1 together. So I've got negative 48 plus 8 gets me negative 40. Negative 12i1 plus 12i1 gets me 0i1s, that's cancelled. Then negative 42i2 plus 4i2 gets me negative 38i2. So from this, I can deduce that I2 must have a value over here so I can see it. Negative 40 divided by negative 38 1.05. And I'm going to continue on with this. And I'm going to substitute for I2 in equation 2. I could use any of them, it doesn't really make any difference. So 16 equals 4i1 plus 14 1.05s. $14.7. Then I'm going to change sign with this one. So going from being positive 14.7 to negative 14.7. So 1.3. And then simplifying that, taking the 4 over, goes from being a multiplier to being a divider. Gets me an I1 value of 0.325. Then my current through my load, I1 plus I2. But actually that's IRL I'm calculating. So 0.325 plus the 1.05. 1.375 amps, and the voltage across the load, the current through the load times the resistance of the load, 1.375 multiplied by 4 is 5.5 volts. The last thing to mention is that you can check these I1 and I2 values using a different equation. So if, for example, I wanted to check them, I know I've used I2 in equation 2, but I could use either equation 1 or equation 3 to check. So I'm going to use equation 1 to check. So 12 times I1, which had got 0.325, plus 4 times 1.05, and I should get 8. And I'm getting 8.1, so that's not bad. And I will double check with my equation 3. That's negative 12 times I1 again, 0.325, minus 42 times 1.05 equals minus 48. So I can be quite confident that these answers all tie in and that that's correct.